In this video, we're going to talk about alternate interior angles and how they're used as a reason in a proof. What does it mean to use that reason? And what makes you look at a proof and realize I'm probably going to need to use the alternate interior angle theorem in the course of this proof? Let's take a look at a specific proof. All right, so here we have a quadrilateral, and we're given that AB is parallel to CD. And you might remember we indicate that with these little arrows, just to say that those two sides are going in the same direction. We also know that AD is parallel to BC, so I can do that with two arrows. And we need to prove that the two triangles are congruent to each other. At any rate, since we have parallel sides here, that's going to give us some reason why we're going to think about alternate interior angles. Whenever we've got alternate interior angles where the two outside sides are parallel, those angles have to be congruent to each other. So let me use my yellow highlighter to highlight the top and bottom side. So to find alternate interior angles, we need to look for what we've been calling the mark of Zorro. So we need to have a Z shape, or maybe a backward Z shape. Can you see some side that would complete a Z shape or a backward Z shape if we also highlighted that in yellow? Yeah, so we've got this diagonal here, and there's a backward Z right there from the two parallel sides and that transversal that cuts it. And so therefore, we know that the two angles that are composed from these three sides must be congruent. All right. So can we say angle B is congruent to angle D in this statement right here? Or is that confusing? No, it's confusing. There are a lot of angles that have B as its vertex. So we've got to use the three-letter form to talk about this angle. And what would be an example of an angle name that would describe that bottom angle? Well, B is the vertex again, so it needs to be the middle letter, and you can either call it ABD or you can call it DBA. Either one of those describe in three letters that angle. And then the top angle would be the same thing. You could call that BDC or CDB. And the reason for that is alternate interior angles. All right. So we've used one of our given statements. We have that this side was parallel, and that led to this pair of alternate interior angles. We've got another pair of parallel sides too. Is that going to lead to a pair of alternate interior angles as well? Let me use my blue highlighter for this. So this is saying that AD is parallel to BC. So is there a Z shape that shows up with these two sides? Well, it sure would be easier if we turn this around so that those blue sides were horizontal. Does that make it easier to see if there's a Z shape in here? Yeah, it does. Once again, the diagonal is going to be the third line that gives us a Z shape there. And so now we know a different pair of angles that are congruent. These two sides make up an angle, and these two sides make up an angle. So those are a second pair of angles. And so once again, we're going to name them. So this angle down here at the bottom, it's going to have B as a vertex. We could call that CBD. And an angle at the top, it's going to be this angle right here. We could call that ADB. And like before, you could reverse these and it would name the same angle, but you need to make sure that the middle letter is always the vertex of the angle. And once again, This is alternate interior angles. There's another case when you can use alternate interior angles, and that is when at the bottom of a proof, you need to prove that two sides are parallel to each other. So maybe I had a proof, I don't have an example of it here, but let's say that the purpose of this proof was to prove that AB was parallel to CD. So I need to come up with some reason to justify that these two sides are parallel. And once again, when I'm looking at a shape like this, a really natural thing for me to do is to think about alternate interior angles. So if I manage over the course of this proof to prove that angle DBA was congruent to angle BDC, then I could justify saying that these two sides are parallel to each other, again, by alternate interior angles. So notice the reason that make you think about alternate interior angles as a reason. In this first proof we looked at, we were given that sides were parallel. And when you're given that sides are parallel, you need to look for alternate interior angles. You might also look for corresponding angles. That's another possibility. But alternate interior angles are more common as things that come up when you know that there are parallel lines. You want to look for that shape. And we can also use it if you need to prove, if your goal is to prove that two lines are parallel, you can do that by showing that two angles are congruent and then argue that those are alternate interior angles. And so those must be parallel lines. So it works both ways. So when you see parallel lines and either you're given or you're to prove, you can be pretty sure that you're either looking at alternate interior angles or corresponding angles. So be on the lookout for using those givens to prove those angle relationships and the congruence based on them.